Hello, once more. Welcome back to the cellar. Now, I've had a couple of questions on the board controller hardware I've sort of shown and mentioned before. So today, what we're going to do is a little bit of an overview of the hardware, what it consists of, how it's put together, circuit schematics, and how I test these things. And we're also going to look at one or two problems I've had because, this is Leopard Street. So here we are. This is what I've been up to today. I've had a few questions on what this is, how these things work, why I use them, isn't there something better I can do, yada yada yada. So here we are. This is a board controller. Leopard Street uses multiples of these. This is one I've finished putting together and testing today. This will go into board F, hence the F on the bottom of the board. This is complete overkill for board F. Board F doesn't need all of this, but going with a standard design helps. So before we go into exactly how I put this together, which I'm not going to show you because that would just be incredibly tedious, this is what we've got. Make sure that's all nicely on screen. So the heart of it is this. This is Expressive ESP32 microcontroller. It's basically a small computer with pins designed for controlling things, model railways. You find these in all sorts of gadgets. The reason for using this is this has wireless built in, hence the antenna. You can get them with a little antenna that sticks out the end. I found I was having problems with signal strength when I did that, so I've gone over to this board. So that is the center of this with its antenna. It's this bit. This has a 5-volt supply. It can either come in via the USB socket on the end, which is useful in your programming, and I'll show you that in a minute when I power it up, or this green socket up here, which takes 5 volts and ground. This comes off the layout power bus. We've then got this little circuit here, which is this blue LED. Heartbeat, not the TV series. This is set up to flash on and off every second. So on, off, on, off. So purpose behind that is if that stops flashing, I know something's gone wrong. If that is flashing, I know the software is running. So that makes quite nicely. We have this little screen, which is this little circuit down here. It's 128 pixels wide by 64 pixels deep. OLED, this one's in white. It's small, but it's surprisingly clear to read. I'm using it with some software which I'll show later to basically handle 8 lines of text by 20 odd characters wide. Very simple. Again, this is status information when the system's running. It's on Wi-Fi, so I can see the IP address, I can see the signal strength, and it is just on a little socket. And this is going to be underneath a railway board eventually. These displays are completely optional. I'm using them when I'm developing. I can take them off later. So this has the job of connecting, this basically controls the layout. This has nothing to do with controlling the trains. This is something fairly fundamental I've done with Leopard Street. The train control and the layout control is separate. At the moment they both talk via JMRI, but in a different way. This communicates using the Mosquito protocol, the MQTT, which sends messages backwards and forwards. This receives messages, it does things with them, it sends messages back. So we come on to what else we've got. This little circuit down here, which connects to this socket, is one of these. This is a TLC 5947 pulse width modulation controller. If you're going to use these, tip, they are extremely sensitive to static electricity. I've blown up God knows how many of these things. Slightly modified. They come with a, I think, 330 ohm resistor here. I replaced that with a 10k. This sets the current that will go through the LEDs. This puts it at about 3 milliamps, which is fine. This board can take decent voltage. The reason it's wired up the way it is, essentially this wire goes off to become a 12 volt power input, which has nothing to do with this board. And I've got a little test board here with some LEDs, which we'll look at later. So this feeds in. This uses these serial peripheral interface lines, which come out as lines 18, which is clock, which is down here somewhere. And there's a data input line, which is pin 23, which is over here. And you can daisy chain these. You can connect another one on the other end of it and then connect another one to that and have as many as you like. But that board, as it stands, will control 24 LEDs on or off. And wahoo, there's lots of ways of doing that. This also means you can set the brightness individually, which is quite nice. So, for example, if you've got these lights in buildings, you can set the brightness. If you're using them to control colour light signals, hence the little test board there, which I am using but only in off-scene areas just so I can see what's going on, or I will be, you can set the brightness. So sometimes you find the green LEDs are a lot brighter than the red LEDs. Now you can tone it down a bit on this. It's a nice to have feature. But that can control 24 LEDs, like I say, or 48 if you stick a second one on. And that has a little connector, plugs in there, like that. And then it has the power lead. Now, this would normally be connected. I'll plug this in a minute, because it's going to get in the way if I don't. There's lovely little JST connectors as well, which work rather nicely. This will will have a 12 volt feed. At the moment, it's powered on 5 volts, which is fine for driving a couple of LEDs. Use 12 volts, you can stick like 3 or 4 white LEDs in a row in series, and it will drive them quite happily. The layout has a 12 volt power bus specifically for lighting, so there we go. So that's this socket. Come over to this socket over here, and we have this. This is a PCA 9685, again a pulse width modulation board. These boards, I get them all from AliExpress or eBay. This uses a different bus. This is on the same bus that the screen uses. This is the integrated circuit, or I2C or I2C, there's various ways of doing it. Bus uses a couple of wires here. As you can see, there's some others on here. This short grey wire isn't used when it's on the board. It's only here for testing, because this has its own power terminal. This gets a 5 volt feed, 3.3 volt feed on here, because the ESP32 speaks in 3.3 volts, and if you feed it 5 volts on the wrong pin, it goes bang. Servos want 5 volt. This little board has a separate terminal here. You put 5 volts in and ground in. Leopard Street has a 5 volt power bus, because I was having some problems with these boards. I've modified it again. I've taken a resistor off so that there is these boards by default are enabled. I don't want that. I want them to switch off, not do anything until I tell them to turn on. So I've taken that resistor out and I put a different one on the board, which I'll look at in a minute. This takes commands and it can drive 16 servos. Very, very simple. They just plug in 1 through to 16. You can talk to them, you can set positions, away you go. You can change the address on this if you need 32 servos. You can just solder bridge some of this and maybe take a resistor off, and all of a sudden you can talk to multiple. That's on address 40. Change one of these, you can say, oh, one's on 40, one's on 41, away you go. We'll look at the code for that later. Like I say, it's a 6-pin connector. Only 5 pins of them get connected normally. The board is set up to provide 5 volts on this grey wire to power the servos. I can power a couple of them off the USB bus, again for testing. As I say, when that gets installed, this grey wire will be removed and it'll have its own power feed. Except on board F it won't be, because board F doesn't need one, but we'll come to that. Then we look up here, like I say, I've added another resistor, which is actually under this. There's a, oh no, sorry, no, it's here. If you look here, there's a 10k resistor. And what that does is it takes this output enable line and makes it logic high. If there's nothing connected on this line here that goes off to the ESP32, it says by default that pin will be at 3.3 volts, which will turn the servos off. Controller works, but it turns the servos off. As this board boots up, it says make that pin logic high as well, which comes straight here and keeps it at 3.3 volts. Later on, when everything's finished, it says make that ground. That then goes logic low. There's not enough current flow through there to change that, and that sort of comes back this way. That goes to ground, servos enable. Because I was having so much trouble with this, there is also a 1K resistor and a little green LED, which is down here, so I could see what on earth this output enable line was actually doing. I was having no end of trouble with these servos activating when I didn't want them to, which effectively, I mean, here's a servo. What it means is I want them to move like that, but at startup it was doing that and drawing a lot of current because it hit a stop and it couldn't go any further. That actually forced this board to reset, which was causing other problems, and then it just went into a never-ending cycle of it. But equally, if I connect that to a signal and it goes more than just a little bit, it will rip the signal apart. Points can cope just about, signals can't, so I needed to fix it. Hence this little circuit I put on here and this, so I can see what on earth it's doing. And it's now working correctly. The issue, I think, was in the code. There's something that works on an Arduino, but it doesn't seem to work on these boards, so I'll look at that in a minute. But that circuit, that little bit up there, means I can control 16 servos off this. None of the Leopard Street boards at the moment need more than 16 servos. If they did, this board would have to be modified so it could talk to another one, or I would fit another connector on the other end of one of these and I would daisy chain it, and then it's just a software change. And then finally, we have this little beastie, which is quite interesting. This is the PCF8575. You can get an 8574, which is a 16-pin DIP chip you can put on strip board directly. These you have to use with the little breakout boards. You can't get them in any other format than that. And what this does, it talks to the same bus, so it's talking to the same 2 pins on the chip as everything else is on the ESP. It has another little circuit, which I'll come to in a minute. And this provides 16 pins, if you ignore those 2 at the end, 16 pins for input or output. Now I use these to drive relays with the output. They can't drive much current, that's quite important, but the relay boards have an optive isolator on. I mean, it's relay boards are like this. They've got one of these, so this takes very, very little current to switch the relays. It will also take inputs. Now the inputs are open drain, so effectively, if I just do a little drawing on there, I'll mess that up. I'll do it later. I will go into these chips in a bit more detail in another video. They're good for some types of inputs, but not for others. If your sensor is active low, that is, it normally has a 3.3 volt output or a 5 volt output, this will work. And then when it senses something, it drags it to 0. This will work. If it's the other way round, like a lot of the infrared sensors are, if it goes high when it's active, this won't work because of the way the board works. Essentially, these pins are kept high, and if you drag them down, it knows it's gone to 0, and if you don't drag it down, it's at a 1. That's one of those. So as I say, I've used this. The software is set up to put these 8 pins here are for driving relays. These 8 here are for inputs, and I can plug one of these when I build one into it directly, and it will just pick the inputs up and it works. It's brilliant. Again, you can connect multiple of these, which is why I've got 2 sockets, because some of these boards are going to need more than one of these. And this is the beauty of this. This has this little interrupt circuit, and this is this has a 10k resistor to pull this line to be logic high normally. You can do this internally in the ESP. I just like to have physical resistors on here because I know what I'm doing with that. And then if this chip has something to say, it will make that pin go low and your microcontroller can see it. So instead of having to check 8 inputs in code and say, have any of them changed, all you do is you look at this pin here and say, has that pin gone low? If it hasn't, forget it, nothing's changed, past you go. If it has, then you ask this chip, what's your data? And it'll give you a 16-bit value back, and you can then see which bits have changed. Quite useful. Again, you can have a few of these on the bus, and they can all use the same interrupt line, and if any of them squeak, you ask them all, or you can give them all individual. Here I've set the sockets up for 2 of them. They'll both use the same interrupt line. When I get that far, I'll have to change the code slightly to say, instead of downloading one, download both, and they can plug in either. And that is essentially the board controller. So if I start plugging some of these bits in, we'll switch it on and I'll show you what it does. So that goes into there, and that goes into there. I can plug a servo in over here. This board is set up to drive this one as a test servo. And I have this here, which, to make sure I get these the right way round, this is always a slight problem. The cables really don't like behaving. This one comes in here. Now obviously these are all on little boards. The idea is they get screwed to a wooden panel. That'll have to sit just off to the side somewhere, probably over there. I will plug that in up here. The whole thing is then going to get twisted sideways, because if I don't, I can't plug it into the USB. So you'll have to forgive the mess at this point. Put this over a little bit, you'll be able to see what we're doing. So let's switch this on and see what we can make it do. I'll just find a way of making sure this USB cable isn't trapped on anything, and then pick up what I've just knocked over. So that goes in. Pick up a little pot of paint. And here we go. Going to work? No, it's some reason it's going into reboot mode constantly. This was working a minute ago, so I'm not quite sure why. Let's unplug that, so that works. Yeah, now it's powered up. It's objecting to the current drain of the relay. Sorry, the servo, which is fine. Now we're switched on. What we've got is, for some reason, the lights are all on, which I don't think they should be. In fact, I have a horrible feeling I've blown this board up now as well. Let's just try some of these. This was working a minute or two ago. Yeah, so, yeah, okay. I might have to come back to the LED board. I may have just killed that. But if you look down here at this screen, how easy that is to see, what we've got, board F, Wi-Fi, signal strength, IP address, MQTT OK, so we're talking to the MQTT system. TN is turnouts, which are the servos, so that is talking, it says servo there is closed. So what I'm going to do is I am going to try and get my other software working properly. For some reason it doesn't necessarily always want to. So I take that, I say I want turnout F0. You see the little green LED is on here, so this should be active. Type in thrown, which is the magic keyword. Hit publish. Hit publish, and for some reason, hit publish. Sorry, F0. Doesn't need to be F0, it needs to be F1. Sorry, my mistake. That servo moves. Turn that back to closed, and servo moves again. JMRI can send thrown and closed. I've added another one which JMRI can't send, but this board understands. I can say mid, and it will move into its defined midpoint, which may not necessarily be the exact middle. It's just the way these things work. But what that means is I can tell this to set these to midpoint. I can plug the servo on. I can stick the arm in quite nicely. For reasons best known only to itself, hopefully I've not blown this board up. That would be quite frustrating because I've literally only just assembled this. These should go through a little light test and then should turn off, and it appears for whatever reason that I've managed to blow that board up. joy. Anyway, so let me just try that again with some lights. So if I try and turn one of these lights off, yeah, literally that was working about 5 minutes ago. Now it's not, so I've probably blown the board up with static electricity. Brilliant. Anyway, I'll sort that out off screen. And we have this little board here, and to test this is relatively straightforward. What I do is just take a little piece of wire, I connect it to that pin, which is ground, and then what I do is touch one of these. And if you look at the screen, you can see numbers are changing. And in my MQTT system and in my JMRI system, that will tell me a block is occupied, block isn't occupied, block is occupied, block isn't occupied. When it works, it's quite good. It is extremely frustrating with these board controllers. I've used them before, I've not had any problems. Now I'm using them in the cellar, they are turning into an absolute nightmare. Just try it again. It's programmed, I mean the light shouldn't even be on at the moment. It's programmed to run a light test and then turned off. That's because we're going back into constant reboot mode. This is why I use the separate power supply in the end. So yeah, that's a board controller. Yeah, so the next thing to do is probably just have a look at the software behind this if you're interested, which I will do in another video because this one's already getting a little bit longer. But essentially this is how I'm driving Leopard Street in terms of the layout. Control comes into this to set points and turn lights on and off when it works, and the block detection boards are fed into here. This feeds them back into JMRI, back into MQTT, and the beauty is once it's in Mosquito, anything can talk to it, which means in the not too distant future I'm going to be doing some experiments with automation on the layout, and I'm going to be having another piece of software talk to MQTT to find out what's where, or at least find out where something is, and then talk to JMRI via the Wii throttle interface to say make this train move, and listen to what's on here for when to stop the train and when to change the points. That's the idea. So that one's coming up, but that is just a brief overview of how these board controllers work, or don't work in the case of this lighting board, which is increasingly frustrating, it must be said. I might have to have a look at that. There might be another way of doing these boards. And that's that. So yeah, I will catch people in the next one. Thank you very much for watching. Likes, subscriptions, and yeah, likes, subscriptions, shares, all the usual gubbins, comments more than welcome. And yeah, there we go. Thank you very much, and goodbye. Now, this is editing me again. Shortly after I completed this, this was videoed Saturday afternoon, I had a little bit of a think in the evening, and I think I've worked out what was up with that TLC lighting board. So there will be a follow-up to this when I have a few more experiments and try and get those things working. I've used them before, I've not had these problems, so this has got to be something I'm doing here. Anyway, I will catch you around soon. Thank you very much. Goodbye.